Hello, everyone. My name is Devendra Kapadia, and I'm the manager of Calculus and Algebra at Wolfram. And I welcome you all to this first Twitch session to show you the new features of version 12. So the plan is that in this presentation, I and my colleague Itai Seggev from the Asymptotics team will give you an introduction to this wonderful set of new functionality in version 12. This is a developer talk. We are both developers for the functionality. So you can ask us whatever questions you think you want to ask. We'll try and do our best to answer them. And we'll try and keep it as informal as possible. And the plan is that I'll first run you through the whole page, the features page, and show you what we have done in a broad perspective. And then you'll have a chance to see a demo from Itai. So the first question is, we're talking about asymptotics. So what is asymptotics? Well, to me, asymptotics is a third mode of computing. So traditionally, we have had symbolic computation in Mathematica. So things like integrate and desolve and sum and rsolve, which everyone loves. And for some people, that is the classical Wolfram language idiom. But of course, we also have the numeric solvers, particularly ND-solve, which is now become very popular thanks to nonlinear FEM and that kind of stuff. So the question is, do we have something that falls between the exact symbolic computation and the approximate numeric computation? And that's what asymptotics is. It's a way to combine the best of both worlds. And asymptotic methods, of course, are used all over the place. If you go to number theory, they'll try and approximate the prime number sequence. You go to computer science, and one talks about the complexity of algorithms. Go to statistics, and they'll talk about the central limit theorem. Go to physics, they'll talk about Feynman diagrams. So everyone today uses asymptotic methods to try and find this kind of golden mean between exact and numeric. And the point is that this kind of method will let you crack pretty hard problems, like, boundary layers and turbulence can be solved at least partially with these methods. And the key point is that these methods are very insightful. So what do I mean by that? Well, what happens is that with asymptotics, we give a very simple formula that kind of captures the whole problem. So you don't have the exact formula. You don't have just a numeric approximation. You have a simple formula that tells you exactly what's going on. And so with version 12, we've actually brought this whole area live. We have a full range of asymptotic solvers for all kinds of things, sums, differential equations, etc. And let me first give you a kind of list of things that have happened for this version. So we have, to begin with, the relation functions, which compare f and g and tell you which one is larger or bigger as you approach a certain point x naught. So that's the kind of thing you talk about in, let's say, computer science, big O and little o, etc. We also have a function for differential equations requested by people all over the world. We have functions for integrals, difference equations, sums, and algebraic equations. So pretty much what you have over here is a mini course on asymptotics for anyone who really wants to learn the subject. So let me begin by giving you a broad overview of the page. So you can think of each row over here as being a section in a Mathematica notebook. And in fact, that's what they were. We prepared these sections, we brought them together, and that's how the web page went live. So the first section, the first row over here, is about asymptotic relations. The second row is about differential equations. We have a single function, asymptotic desolve, right, that does that. The third row is about integrals. The fourth row is about difference equations, rsolve kind of things. The fifth row is about sums. And the last row, and perhaps the most beautiful and modern function for us, is the asymptotic solve function, which does algebraic equations. So that's the layout of the page, one row per feature module. And of course, if we want to dig deeper, we have the function pages. There's asymptotic desolve value, which has received the most testing. On my estimate, with the help of interns, I've tested around 4,000 examples with this function. And then all the other functions which have also received a lot of care in preparing nice examples. So the function pages are the place to go if you really want to dig deep into these functions. So of course, if you really want to start out, you might be best off just going to the guide page, looking at all the different functions and clicking your way and enjoying the wonderful new functionality. And notice that we also have the limit functions over here, which were introduced in 11.2, and they are the place where we actually began our asymptotics journey. Okay, so beyond that, we have been very good about writing blog posts. So Itai wrote a nice blog post about asymptotic relations. I wrote one on asymptotic expansions. We've given several talks. And in fact, I also gave a webinar some time ago on the 11.3 asymptotics features. That was a wonderful experience. So it's a good point for me to tell you that we actually have another set of version 12 webinars coming along very soon. And I strongly urge you to go for that set of events. They are great places to interact with other people. They're very lively, lots of questions, lots of interaction, lots of suggestions. So do keep this in mind along with the Twitch sessions. And of course, we have all the other feature pages which are kind of close to us. Core calculus, things like finite elements. We do have a good interaction with the PD folks. So that's the broad overview of the page. And I just want to dig a little deeper into one example per row. So for the first row for asymptotic relations, I'm going to look at this example for asymptotic approximations. And the function over here is asymptotic equivalent, which compares, in this case, the factorial sequence and the Stirling approximation. Now, Stirling's approximation was discovered by Stirling in 1730, but in fact, the history is that Abraham de Moivre discovered in 1730, but he could not fix the constant in the formula. And what Stirling did was to identify the constant as being square root of 2 pi. And you might say, oh, well, that's not too important. But if you work in asymptotics, you realize that the constant is everything. So he who nails the constant gets the prize. So this is Stirling's formula, thanks to his discovery of the square root of 2 pi constant. So when you say equivalence, you mean that the ratio of things becomes 1 as you go to infinity. That doesn't mean that the differences become small, but the actual error, the relative error, becomes very, very small. And you also have the prime number theorem with lots of different ways of approximating the prime pi function and a numerical table over to show you how nice the approximation is. So asymptotics is really very powerful and versatile, a wonderful way to explore our universe. Okay, on to asymptotic desolved value. So this is in fact where things began. So probably around 2006, Stephen Wolfram asked me to implement a function for series solution differential equations. So here's a simple example from a kind of college textbook where we try and solve the differential equation for the cosine function. And you can see over here that if I take a small number of terms, I get a pretty decent approximation. But then as I increase the number of terms, I get a better and better approximation. And that's a typical textbook picture of series solutions of ODEs. Now, because we are in the case of what we call an ordinary point, things work wonderfully, and you can do systems, you can do nonlinear equations, you can do what you like. But as Itai will show you, you can go much beyond all this and do Frobenius series, asymptotic expansions, solve boundary layers, etc. On to integration. So we have the classical methods, we have the Laplace method, we have the stationary phase method, and this over here tells you why asymptotics is such a kind of strange area. So here's an integral, and that integral is quite easy to actually evaluate. But if you try and do series expansion over here, you see that it diverges for every value of x. And that's very typical of asymptotic approximation, that they diverge, but they still give you excellent approximations. Now, we are brought to think that more is better. So if you take more terms, you get better approximations. But over here, if I increase the number of terms, things go wildly wrong. So that's what the picture over here shows you, that as you take different values of x, you get different ranges in which you have a good approximation, and then things just blow up. So that's integration. And there's also an example over there of Feynman's first integral for applying differential and integral sign, which works really well. Okay, so on to difference equations. So that's the row for difference equations. Now, here's the example that I'm going to take up, and there's a bit of history behind this. So you see, Poincaré did the asymptotics in this area first. Then Birkhoff and his student Trzynski followed, and they wrote two very difficult papers on the subject. In fact, Trzynski worked right here in Champaign-Urbana, so about 1.5 miles from Wolfram. And their papers were still very difficult to read. So around 1985, Doron Zeilberger and Jet Wimp wrote a very nice paper, which they called Resurrecting the Asymptotics of Recurrences. And they complained that American mathematics had lost this touch with asymptotics and a need to come back. So that's a paper that really inspired me. And this example is from that paper. So basically, you have a sequence, the sequence of involutions, which are permutations which are their own inverse. And before version 12, all you could do is to apply find sequence function and find the recurrence. That's okay, but not so interesting. But if I now put a decimal point over here, then I can call this new function asymptotic RSOL value. And you can see over here that you have a constant, but that constant is now just an approximate constant. And so Stirling was right, and that constant is the hardest part to actually find out. Okay, so you see the approximation is still pretty good at even n equal to 1000. So this example shows you the power of asymptotics. You start with the sequence, find an approximation, and then use it. Okay, on to sums. And this example over here is from a paper by Philippe Flageolet, where he talked about the Mellin transform and harmonic sums. So that's what he would call a harmonic sum. It's got an exponential in it. And this expansion over here actually comes from a Mellin transform computation. So for version 11, we implemented the Mellin transform, and I wondered how useful it would be. But the point is that the singularities of the Mellin transform actually give you the coefficients in the power series over here. So that's a very nice picture with our brand new complex plot 3D function. Okay, and finally on to algebraic equations. So here's the example for this row. You have an algebraic curve. It's got two variables, x and y. You give it to asymptotic solve, and you say, give me all the kind of branches of the solution from the right, from above. And you can see there are 6 branches, 1, 2, 3, 4, 5, 6. And there are 4 on the left, so to speak, 1, 2, 3, 4. So what's happening? Well, what's happening is that you have an algebraic curve, and that algebraic curve has a singularity. So when you write over here, you see there are 4 branches on the right, 6 on the right, and 4 on the left, and together you've got 10 branches. And so in a way, what you've done with this calculation over here is to kind of blow up that singularity. So that singularity is now gone. It's replaced by 10 different directions, and you can go where you like and explore the curve. So this is by far the most deep and profound part of version 12, Asymptotic Solve. It solves lots of user questions as well. So that's the final piece of functionality I want to speak about. So asymptotics in version 12, thanks to the efforts of the team members, there's Roger Germanson, there's Itai, there's Adam, and myself, and other people helping us out with benchmarking, has become a really powerful tool for our users. So maybe that's a good point for me to stop and let Itai continue, but do ask questions and do let us know if you have any suggestions for the functionality. So I'll stop over here. Thank you.
Okay, well, thank you, Devendra. I will hopefully be sharing the correct screen. And yep. Okay, so you see a browser window and the Mathematica notebook, because I'm going to be sort of splitting my time between them, and just showing you more of these examples, and also maybe trying to talk a little bit about various additional things you can do with them. So starting with asymptotic relations. So very famously, perhaps the first place most people encounter asymptotics is in an analysis of algorithms course, and they learn about big O. And I'm just going to make sure everybody knows. So all these inputs on these pages, you can just click on them. It's copied to the clipboard, and then you can paste them in and evaluate it. So we see here, we're comparing, we're talking about the famous traveling salesperson problem. And there's the sort of naive algorithm, which tries all n factorial routes. And then there is the Held-Karp algorithm, which improves that to roughly n squared times 2 to the n steps, which is clearly faster. But, and I'm going to also copy this input. They're sort of in the same general complexity class called X-time, because if you compare n squared 2 to the n with 2 to the a times n, assuming a is greater than 1, then it will tell you that these are big O of each other. Asymptotic less equal is big O. If I had said that a is equal to 1, it would say false, because clearly n squared 2 to the n grows faster than 2 to the n. And if I didn't have any assumptions, then it will tell me, well, it's true, assuming a is greater than 1. So, I mean, there are different ways of handling assumptions. In this example, we chose to just give the assumption we knew was needed in order to give you a simple true answer, but we didn't have to do that. It could have just told us 2 to the n. Excuse me. It's spring and my sinuses are going crazy. Right. So now you can't get away with just a simple linear constant if when you want to compare n factorial, because n factorial goes greater. So this is little omega here. But since X-time allows polynomials in the coefficient, you can just compare n factorial with 2 to the n squared, and that gives you true. So n factorial is big O of 2 to the n squared. And in fact, as is very often discussed, any factorial is any polynomial is less than any exponential function. Exponential functions grow faster than polynomials. So that's about comparing algorithms using our asymptotic relations. Our second example is about finding the computational complexity, and it uses the Strassen algorithm for fast matrix multiplication. It was the first subcubic matrix multiplication algorithm found. So you split up your matrix into 4 submatrices, you form 14 linear combinations, you multiply 7 pairs, and then sum the 7 results. So that means the time to do something will be some constant b to split the matrices, some constant n squared for forming linear combinations, and then 7 times whatever the time is to do matrix multiplication of a size n over 2 was. So that's a recurrence relation. We give that to our solve value, and it gives us some complicated relation here. And maybe I should copy these two as well and just show you. But as is often the case, we want simple, just deleting order. So this is the same order as just n to the log base 2 of 7. And so what were the assumptions I put in? Well, that the time constants were positive, and also our arbitrary constant of integration, or I guess of summation, since we're doing RSOL value, was also positive. And these are all pretty simple things, pretty obviously true things. So log base 2 of 7 is less than 3, which means this algorithm is faster. Then our third example is talking about how you can do things in higher dimensions. And here I'm going to cheat a bit just because the inputs are kind of big. Copy them from a page I have here. And so we're going to compare two functions, f of z and g of z, near the point z minus 1 in approaching it in various directions. So what are we computing? We're computing, is f little omega, is it asymptotic greater than g of z? And when we approach in the direction minus 1, it's true. In the direction I, the direction 1, it's true. So all of these, it's true. These three directions, it's false. And to help us understand what those directions are, I'm going to create a manipulate here. So I've put in a plane at along the real axis, and so we can see that this axis here on the bottom is the real direction. So if I pause, whoops, no. So if I pause here, so this is the direction minus 1, and that means we're approaching minus 1 from above. And so when you give any numeric direction, it means think of you're approaching 0, moving, or I guess think of your tangent direction in the complex plane being that number. So here's minus 1, you're approaching, moving towards minus 1 from 0. I always find this incredibly difficult to remember, so I will take this asymptotic greater, which was right here. Right, so this is direction minus 1, but I can't ever remember that because it's weird that from above is minus 1. But fortunately, if you just type it in, then, and here, actually, let me type it in so you'll see it. So we have auto-completion, and we have synonyms for +1 and -1, which are from above and from below. So from above means -1. And we see, so we see in the upper half plane, we have it true. In the bottom half plane, it's false. And so that tells us if we were to say direction goes to reals, which means approach from both real directions, so the same thing as from above and from below, well, that's still true because it's true on both real axes. But on the other hand, if you were to say direction goes to complexes, which means approach in all directions, whoops, I mistyped it and it told me that. It says direction this is false because it's not true in all directions. It's false when you approach in these directions, so the overall answer is false. So that is this example. So Devendra took you through this example already, so I don't need to do that. And yes, Devendra did this one as well. So Frobenius approximation. So we have we have a sort of a linear a linear ordinary differential equation, but with singular points. Our coefficients are going to go to 0. But we can still find some nice approximations. Now, if since it's a second order differential equation and we haven't supplied any initial conditions, then we have 2 arbitrary constants. So if we set one of them, and if we look at our solution right here, we can see one of them is multiplying this whole first term with square root of x and other positive terms, and the other one multiplies this expression with sort of the complementary multiples of 1/2 and starting at -1/2. So if we set the C1 to 1 then and C2 to 0, we'll get a nice finite solution. But if we do the reverse, we'll get something that blows up at the origin. But of course, I can set these numbers to whatever I want them to be, and they'll still be solutions. So here, this blows up towards -infinity since I sent C2 to -1. This one blows up to positive infinity, but is sort of offset from where our original term was. And this solution points out, this is another nice example. I think I'll just use it. So we're solving a 4th order solution in which we get some asymptotic terms. We get some logarithmic terms, and we see 4 constants of integration since it's a 4th order equation. But one of the neat things about this particular example is that in this case, the asymptotic solution turns out to be the exact solution. So without having to by just doing a series solution, we ended up with getting the exact answer. So that's kind of nice. Obviously not a usual occurrence, but it's nice when it happens. Okay, generate in the next example. This one's kind of long, so rather than doing it interactively, I'll just sort of talk you through it. We have another linear differential equation with some singular coefficients. And we compare sort of different orders of the approximation. This is, in fact, here's the ODE for the Airy equation, which has, and we find some nice solutions of that. Again, it's singular. We get some blow up in these different terms, and an exponential out front. If we compare with the series for the Airy function, then we find that, well, our 2 terms are actually just sort of the expansions of Airy AI and Airy BI. And so we found sort of the general solution and where those 2 Airy equations come from. And this is a higher order equation that we can, again, solve. A 3rd order equation, we get 3 constants of integration. Sorry, I skipped over this visualization a bit too quickly. So this visualization shows us Airy AI and Airy BI along with the two halves of the approximation we got, where we set one coefficient or the other to 0. And we can see that sort of for small values of x, they don't super agree with their friend, but especially since there's blow up at 0, but very rapidly around 1. And since we're doing the approximation around positive infinity, so 1 is a pretty small number compared to positive infinity, we get excellent agreement between the exact solution and our expansion. And I'd also like to just give a little shout out here to dashed lines, which is one of my favorite plot themes. It chooses a different dashing pattern for every function you plot, which makes it just plain easier to see when you have a bunch of different functions. It's also, if you have any color blindness, then, well, even if you're completely colorblind, you can tell the curves apart because each one of them has a different dashing pattern. So that's a great plot theme to know about. How am I doing for time? I'm doing great for time. So next example. Okay. So let's walk through this example a bit carefully. So we have this. This is a slightly different because this is a slightly different example. The previous one is we had a single equation and we found approximate solutions to that one equation. Here we have an equation with a parameter in it, and we're going to, so we're doing a perturbation problem. We're expanding around a particular point and seeing how the equations change. So if I say P sol equals asymptotic D sol value of this equation and y of x, x. So this says, right, so our independent variable is x. We want to solve for y of x, and then our perturbation parameter is epsilon, and we want to expand around 0 and ask for one term in the expansion. So this term has no epsilon, this has one term in epsilon, so there's our one-term expansion. Now we can also, it so happens that this equation can be solved exactly, so we'll just solve this equation using D sol value, again solving for y of x. And then now we're going to compare the two, and so I'm going to not use what's on the build page, but sort of something copied in. So we're going to plot the approximate solution and the exact solution for 3 different values of the expansion. Now there's this weird transpose thing in here. That's because when we substitute in for epsilon, we're going to get a 2x3, a 2-row, 3-column matrix of 3 solutions of the 3 approximate solutions, 3 exact solutions, and I'm going to transpose that so we pair each approximate solution with its corresponding exact solution, and then plot those. And you can see there's a little bit of difference right here. You can see these are the larger epsilons, are these, for this larger epsilon, you can see there's a little bit of space between right there, a little bit of space right there, but pretty quickly they all sort of converge together. And this color data of 106, so every plot theme has an associated color data entry for the different curves. So color data 106, I just happen to know, is the default color scheme for plot. So this is the color for the first curve. This is the color for the second curve. And so this way I made each pair use the first 2 colors. In the build page, I just put in the actual colors, but here's your little bonus feature for coming to this Twitch talk. That's how I actually figured out what the color is, rather than sort of trying to unformat the plot and figuring out what color is embedded. That's how you get those colors. Okay. So our next example is now about integration. So again, we're gonna, we're going to enter a function and we're visualizing it. So here's our function. It's very strongly peaked around 1. And so we want to find the area under this curve. And so we can do asymptotic integrate f of x from 0 to infinity. So we want the integration, we want the area underneath the whole positive reals, and we're going to expand where where our parameter is very large, so it's strongly peaked, and we're going to ask for one term in that expansion. So there's that solution, and we're now going to plug in a value for omega, where so close to infinity in this case means 30, and we get that answer. And if we were to just call and integrate, we see, within a percentage point or so, we have the correct answer using just, just using one term. If we take this and change the 1 to the 2, so we get one more term in our expansion, and now we plug in again, whoops, %/dot omega goes to 30 dot. Then we get within, machine precision, so the 6 or so display digits of machine precision, we get the exact answer. So again, this pretty quickly gives us good solutions. Okay, this one is sort of very similar. We have, here we have, rather than a strongly peaked integral, we have an oscillatory integral where we, the positives and negatives cancel out. So only sort of near the maximum, the absolute maximum, do we get a contribution. If you're a physicist and you know about least action, and you get the main contribution to your Feynman path integral using stationary phase. This is exactly that idea. So we do again an asymptotic integrate of our integral over the interval 0 to pi. Omega is very large, and we ask for one term, and we get excellent agreement with just doing numerical integration. This one Devendra went through. I thought I might give you a slightly different take on this plot. So what this plot is showing is the sum of the absolute value of the terms in the expansion. It's sort of measuring how how the magnitude of the how the series itself just blows up. In this case, since we have an exact answer, a different and if you don't have an exact answer, this is sort of the only visualization possible. You look at the terms and you say, okay, is this converging well or not? In this case, since we have an exact answer, there's a different visualization possible, which is how does the exact answer compare with, the approximate answer? So here, I have probably t has a value at the moment. Yes. Okay. So there's the exact answer to this integral. So here I'm going to basically sum the terms in the expansion, and I'm going to divide that by the exact answer. So we would expect that to be close to 1 if it's a good approximation, and then I take the absolute value of that. And so we see that for x equals 2, 0.02, excuse me, then there's a little bit of wobbly right at the beginning, and then it's really close to 1 for a while, and then it starts wiggling about like crazy and going off to infinity. For x equals 3, it's a similar pattern, only it takes a smaller number of terms for you to get all wiggly and blow up. And we see the same pattern with 0.4, 0.5. So the farther you get from the base point, the fewer number of terms before your solution starts blowing up. So that's an interesting alternate take on this same example, which is to take nothing away from the example as it is. This is, Devendra briefly mentioned this example. So we have an integral, which is slightly hard because it's a logarithm of a cosine, and you have a symbolic parameter inside, which makes it even a bit trickier. And so you ask for, say, 10 terms, and it very quickly, in under a second, gives you one term. So the fact that it only gave you one term, well, maybe terms 2 through 10 are just 0, and then if you ask for term 11, you'd get something. But in this case, integrate can do the exact integral, and so the exact integral is what we got from our one term in the expansion. And this is, again, as Devendra mentioned, this is an example of integrating under the differentiating under the integral in order to come up with an answer. So this is, again, not your usual case, but these sorts of neat examples where asymptotic expansions give you an exact answer. Okay. All right, so let's, so asymptotic R-solve value. So this is, again, we're dealing with indefinite, right? We don't have initial conditions because we're doing this asymptotic expansion business. So if we just click to copy this, we see we have two constants of integration, C1, C2, and so we can just sort of plug in different values. I will, so here we've plugged in a few different answers, a few different values. We can tweak them some, and we get a pretty plot out. So each one of these series is the sequence you get out with those values of the parameter. This next example is sort of a similar sort of example. I'll click to copy this, and so we get one solution out. We have an arbitrary constant from our first order difference equation. So we'll plug in an arbitrary a value for our arbitrary constant, and okay, that's interesting. So, and then here, so in the previous example, we were plotting just different solutions. We didn't have an exact solution. In this case, well, we still don't have an exact solution, but we can use recurrence table to basically approximate the correct answer. And so I'm actually going to change this and say, instead of using 1, I'm going to use 2. And so instead of 1, we're going to use 2 here. And what did I do wrong? Those don't look like they line up. What did I? Oh no, this isn't the one I should have. Yeah, I should not have changed that one. Right, so this is just plugging in the initial condition from the approximation into the recurrence table. So here we just want the first term. Yes, it's the constant we wanted to change from 1 to 2. And then we have a bunch of options just to make the label look right. And you can see that basically the exact solution and the approximate solution are right on top of each other. So we get excellent approximation. Okay, and so our next example is a again, just like with with differential equations, where we had finding solutions to individual problems and finding solutions to families of problems by perturbations, we have that same situation here. So here's a perturbation problem. It's our solve value with this equation, and we're going to solve for y of n, and then we have a parameter epsilon that we're going to expand about 0. Notice that our y squared term here goes away and at 0, so it's a sort of a singular point, and we're going to ask for the first 3 terms in epsilon. So now we're going to plot the solution for different values of parameter, and we see that in all cases it tends to, these approximate solutions tend to decay at infinity. So however, if we do a comparison, then so here I'm going to make a table where I compare epsilon, the value of our perturbation solution at 50, and then sort of numerically integrate our equation at that value of the parameter at 50. And we see for small values like 0.02, then yeah, there's really good agreement between what the perturbation solution said and what the exact, and what the numerical integration gives. But above a certain point, then you get the exact solution is blowing up at infinity. So there's some sort of qualitative change in behavior that's missed by the approximate solution, which is sort of one of the dangers that you always have to guard against. And here I'm going to plug in 0.08 and 0.09. I'm going to just add them into the table here. So I did that in the wrong order because I want decreasing values. Right, so you can see 0.09 blows up. 0.08, there isn't any longer such great agreement between the exact and the numerical, but at least you can see, well, it's not really blowing up. And if you were to extend the number of terms, so change this 50 to say 100, then, well, you'd get overflow, but you'd see that the exact solution is in fact going to 0. If I want this to be a meaningful comparison, I need to change that 50 also to 100. So you can see that, it's pretty meaningful, it's clearly going to 0 at infinity, and this is clearly blowing up at infinity. So the change is about 0.086, which, I discovered by plugging in values and seeing how things behave. There's perhaps an exact analysis that will give you that number, but I don't know what it is. And I see I'm running a little on time. Devendra gave you this example. I will skip this example in the interest of time, but yes, it's just showing asymptotic sum. We have a sum, and this is an indefinite sum here. So we have an arbitrary constant of integration, or summation rather. So we're going to sum in k, we're going to expand about infinity, and we're going to ask for 10 terms. So there's the largest term, and then ever smaller terms because we're expanding at infinity. And here's a little table. The code seems to be missing. I'll make sure that gets fixed. But a little table of different sums and their expansions. Here we're doing a definite sum. So we're going to sum k factorial from k equals 1 to n and do a table for different values of n. So we can do the same thing here. We're doing an asymptotic sum. We're summing k from 1 to n, and then we're going to expand n around infinity and ask for one term. And you can see that we get excellent agreement between just doing the sum and doing this expansion and plugging in n equals 100. So Devendra took you through this example, so I can skip it. This one is kind of a nice example. I will walk you through it. So we have a function and we want to integrate it. And we can do a simple Riemann sum using the right hand rule. And since we're summing from yeah. And then so we get some answer, we get a sum, we make a table of value for different values of n, and we compare this last value with the exact integral, and we see excellent agreement. We could also compute the limit of these Riemann sums as n goes to infinity, and we see, thankfully, that that's the same answer that integrate gave us. We could also use a trapezoidal rule that gives us a different sum, and this gives you sort of much faster convergence. And here is a plot. So this is comparing sort of the trapezoidal rule sum with the Riemann rectangular sums, and you can see that it takes a much smaller number of terms for the trapezoidal rule to give you the exact answer, or converge to the answer. Okay, so this one I am going to click to copy. So here we have a function in two variables, and we're going to find its a solution to this function equals 0. Sorry, this is a function in three variables. And we're going to find a level set of it, basically f equals 0. And sort of by the inverse function theorem, we know that locally a level set is going to be a surface. And so, and since this is a 3D example, I figure it's probably worth plotting it and letting us see. So there's so we're expanding around the where xy is 0, 0. So we're expanding around the origin, which is obviously our center here, and then we're sort of showing the error between sort of this approximate solution and exactly solving the solution. So you can see that near 0 we have 10 to the 6 level, 10 to the minus 6 sort of level agreement, and then by 1/2 or so we're talking close to order 1 error, or at least order -1 error. And then Devendra showed you this pretty cloverleaf example. And this one, let's see if we can get through this. And so we see again direction from above rather than direction from below, and hopefully if I, from above, if I change this one to -1, then we get the same answer. So I was not lying earlier when I said that from above is from above, and from below, that from above is -1 and from below is 1. And let's just click to copy. So here we're solving an equation in 3 variables, and we're expanding in just y and z. And so that's going, and sort of where these intersect give us sort of nice space curves that you can see here highlighted. And our last example is sort of very similar, only we're rather, well, it's again a 2-dimensional example rather, but rather than expanding at a finite point, we're finding a solution near infinity. And so you can see, again, pretty quickly, you know, here's 1.5, you know, and sort of, but certainly by 2, sort of our exact solutions and approximate solutions are completely lined up. And so those are all the examples on the page. I did see that there were some questions on chat that hopefully Devendra was successful in answering. Is there yeah. Yeah. All right. Cool. So those are all our examples. Devendra, do you want to? I will pause for a few seconds to see if anybody from the live stream wants to ask us a few last-minute question. And if Devendra, if you have any final words before we wrap up, now's your chance.
Thanks, Itai. This is a wonderful, very complete presentation. I should say that the examples were really polished and put in final shape by Itai. He's put in a lot of work, so he knows them better than anyone else. And what he saw is the examples from a very closely seen viewpoint, and I hope you enjoyed it. This is wonderful functionality, but we plan to develop a little more for version 12.1. So do let us know what you think we should add to Asymptotics in the near future. But thank you for coming over here. It's nice to see people coming for this kind of a kind of demo, and it was a pleasure to be with you.
Okay. And yeah, I see there's one last question on the chat here about, are there any functions that work directly on asymptotic classes? And the answer is no, we don't really have, oh, I see we don't have that sort of, you can ask, are these two guys equivalent to each other, but we don't have something, you know, is O of F plus O of G, O of H. And we certainly don't have something like the named complexity classes. It's certainly an area we're interested in. It's one of the tricky things is that there's so much implicit notation. You know, the notation assumes a context that we can't necessarily assume when you're typing something into the system to compute. But it's certainly something we're interested in, and something we may have more to share about in the future.
And just one more remark again, that just to thank the people who came here, and also the team members who put in so much effort. There's Roger and Adam and Itai and Henry, who helps us to benchmark. So I hope that you really see the depth to which we have managed to go in just one release. And like Itai said, we'll be working more to do asymptotics, but in a way, it's a difficult field, so we are progressing slowly. Thank you.
Thank you very much, everyone. Bye.